Alright, so hello everybody and welcome to this live class number 97, where we are going to be talking again about some concepts related to machine learning for robotics, specifically the Cummins algorithm. So yeah, welcome everybody and let's start. Let's go. So hello everybody, welcome to this live class number 97, super close already to the live class number 100, which is quite exciting, let me say. But today we are on live class number 97 and we are going to be talking about machine learning. So the last live class we did related to machine learning was super successful. Many people watched that video and enjoy that video, so it was a great success. So hopefully today's live class is going to be the same. Then today we are going to focus on the Cummins algorithm, which we are going to see what it is and how it works in a moment. But before anything else, before I keep talking, let me verify that everything is fine. Let me know please in the chat if you can see me properly, if you can hear me properly, if sound and image are working okay. Hello there, Engineering Nations and Push Panshu. Hello, everybody. Let me know, please, if everything is all right in the chat. If sound and everything is okay, so that I can keep going. From what I can see here, everything should be fine. I think my sound and everything is fine, so there shouldn't be any problem there. Yes, says Moga. I suppose you mean that everything is fine? Yes, we can see and hear you. Excellent. Thank you very much, Engineering Nations. All right, so then let's start. So as always, let me get a bit of coffee here from my ROS developer's Mac. And let's go. So, as always, let me start by sharing here my project with all of you guys. So let me share it very quickly here in the chat. There we go, here you have it. And as always guys, just get the project, click on the well, let me know, is this your first live class? Because I can see here many familiar names like Engineering Nations, Der Kapute also. But is this your first live class or you have already experience with previous live classes? Okay, so yeah, as always guys, just click on the link and you are going to receive the project in your workspace. In case you are already logged in, you will see something like this with the ROS Developers Live Class number 97 project here in your workspace. If you don't have an account, just create it. In a few seconds you will have it, it's completely free. Then once you have the project in your workspace, just click on the open button and open project, and this is going to start loading here the project. So meanwhile I will come back here and let me see here. This is my first live class with you, says Amoga. Okay, so welcome Amoga. I hope you like it. I hope you are following the process. So you need to click here in the project I have shared. In the project link I have shared here in the YouTube chat, you click it and then this is going to take you to the ROS Development Studio screen. And in case you already have an account, you will automatically have this project in your workspace, so you will be able to open it and everything as I am doing right now. Then here I have it loading. This might take a couple of minutes maximum, so I will let it here loading. And meanwhile, I wanted to talk about the new courses that we have published. So this week we have published 2 new courses. One, in fact, is about machine learning. So here we have it, machine learning for robotics. So just the previous week, last week, we published this machine learning for robotics, which is super interesting. I really encourage you to have a look at it. You are going to be able to learn about many things, linear regression, logistic regression, which is what we talked a little bit in the previous live class related to machine learning. Neural networks, of course, Cummings algorithm, which is what we are going to be talking a little bit today. Well, you are going to be able to learn many super interesting things about machine learning and more in depth than here in the live class, which is we have limited time, so we cannot go too deep into the concepts. So we have Discourse available in the Academy, which I really encourage you to have a look at it. And also we have published another one. Last week we published the OpenCV course, which, let me see if I can find it. Here we have it. The OpenCV Basic for Robotics. Also super interesting and super important. If you want to work in the robotics field, this OpenCV library is super important for perception, for making face detection, face tracking, people detection, people tracking, etc. Object detection, to work with AR tags. Also super interesting and super complete course here. So I also really encourage you to have a look at it. And yeah, so basically I wanted to introduce all of you to these 2 new courses that we have published just, I think it was Friday from last week. So they are super new. That's why I wanted to talk to you about them, so that you can check them here in the Academy. And here I think, yeah, so this has already finished loading. So now this is going to load my environment for the new ones, you will see. Yes, it's going to open my environment with the notebook and everything. I will show you right now, guys. So let me close all this. Let me have a quick look here at the chat. Hi, hello, Jan. Welcome. Alright, so this is taking some more time, but no problem. I will get just another drink here from my Mac to get some more energy. So all right. Hello, Avinash. Hello, everybody. Hello to all the newcomers to the live class. Welcome, everybody. Let me know, guys, because let me know if this is your first live class or if you have already previous experience with this. Also, are you loading your project? Have you already been able to load your project? I'm going, by the way, to give a refresh here. So has your project already loaded, guys? Or it is still loading? Hello, Thomas Alapat. Hello, welcome to this live class. Mine has already loaded here. I have it here. Here I can see my project already for live class number 97. So excellent. Then how are you guys doing? Has your project already loaded or not yet? Meanwhile, I'm going to set up this. I'm going to make this notebook here a bit bigger so that we can see it better. There we go. Hello, this is my first class, says Thomas. Okay, so I hope you like it. and you learn, at least I hope that you learn something from this live class, which is my main goal. Every live class that you guys can learn something new. Loaded, says Engineering Nations. Excellent. Excellent. So what about everyone else? Loaded, Mechatronica, Avinash, loaded. Okay, excellent. So everybody has his project loaded also. Then let's go for it. So here we have the project for live class number 97. Then for this live class, we are going to be working with a Turtlebot simulation. So in order to start it, all you have to do is to come here to the simulations menu, and then we are going to select from the words list. Here we have a list of many available words that we can launch, but we are going to choose the empty world. So an empty world, and then from the robots, here we also have a list with many robots that we can load, but we are going to select in this case the Turtlebot 2 robot, which is here at the bottom of the list. So we are going to choose this configuration. We are going to load an empty world with a Touchable 2 robot in it. Then once I have this configuration, I just have to click on the Start Simulation button, and this is going to automatically load Gazebo. For the ones who already have been in many live classes, you already know this. But for the new ones, as you can see, this has automatically opened a window here which contains basically a Gazebo simulation. And this Gazebo simulation is going to contain an empty world with a Turtlebot robot in it, because it's the configuration I have chosen. Yes, so here I have my simulation. Let me refresh this to load all the renders properly. There we go. So here I have my Touchable 2 robot in an empty world. I don't have anything here, it's an empty world. Excellent. So I have here my, I have set up already my environment. You have also here the instructions written in the notebook, in case you want to review them. Yes, and this is the final result. So here I have my Touchable robot in the empty world. Yes, then this is all the setup we need to do. So we need to have here at one side the Jupyter notebook, because we are going to be following instructions here from the notebook. And then here at the other side, we should have the Gazebo simulation loaded as well. Yes, so here at the right side the Gazebo simulation, and here at the left side the notebook, so that we can follow all the instructions and everything. Yes, so this is the setup you should have. Then let me know in the comments, please guys, if you are in this point, in this same point. I always insist a lot in this, because let me switch very quickly to my face. I always insist in that everybody has the setup before I start with the live class, because I don't want you to just be there in your places, in front of your computers, of your laptops, just watching the video and watching me talk and do things here. No, I don't want this. What I want you to do is to do the live class with me. Yes, so that you have your project. This is why I'm sharing the project with you guys, because you can open it and then you can follow the live class with me. So you can be listening to what I'm saying, even watching from time to time to what I am doing, but then you can at the same time reproduce everything in your machine. So you can also test all the programs that I'm going to be doing here, generating all the plots that I'm going to be generating here in the Jupyter notebook. So you can reproduce all the same steps that I'm doing. Yes, because this is how you are going to really learn, not by listening or by watching, but by doing by yourselves. Yes? All right, so let me know guys if you are already set up with everything prepared. Avinash says, my first class with you. All right, so I hope you like it. Avinash, I hope you enjoy it. I'm ready, says Michael Trezzi. Excellent, Michael. Thank you very much for letting me know. Okay, so Michael is already ready. He's set up. But what about everybody else? How are you? Are you already set up also with the notebook and the simulation? Yes, no. Okay, Avinash says he is ready as well. Excellent, excellent. So it's your first class, but you are catching up quick, Avinash. I like that. Engineering Nations also says he's all set up. Excellent. Then let's start. So now that all of us are set up, let's start with the live class, guys. So, all right, then today we are going to be learning a little bit about this Cummings algorithm, and we are going to do a practical example with the Gazebo Simulation. Then this Cummings algorithm is a machine learning related algorithm which is used for clustering. Yes? Then clustering can be related or associated with classification, but it's different because the goal in clustering is to identify or discover similar groups of objects in the dataset. Yes? In classification, on the other side, these groups are predefined. Yes? So here we have a classification. Yes, if you remember the previous live class that we did, which was for linear regression, then we had a data set which is represented by all these points, and then we had to find a line, baseline, which defined the data set that we were receiving. Yes, in this case here we have a line which is classifying the data set into two different parts. Yes. So this would be an example for classification, and this would be an example for clustering. Yes? Then the Cummings algorithm doesn't have any information about the input data except some data features like position in space, like x, y, the features that define the data which we are inputting. Yes? Then this data set, which is the input to the system, let's say, it's mapped into clusters. Yes? In this case, we have all this data set, which is represented by the points, and all this input data is being mapped into two different clusters. Here we will have one cluster, and here we would have the other cluster. Yes? Then the number of clusters that we are going to have is specified a priori. Yes? So we specify the number of clusters that we want to have in our system. Then this number, the number of clusters, can be given based on our observation, our experience, etc. Yes? Also, there are some methods or techniques that can be used in order to determine the optimal number of clusters for a specific system. Yes? In this case, in this live class, we are going to be using a method which is called the elbow method, which is going to help us to define the optimal number of clusters for our system. Yes? For the given data set. Then, okay, so we have introduced the data set that we have introduced the clusters, and then another very important point in the Cummings algorithm is the centroid. Yes? The centroid basically is the, let's say that it's the point which represents the minimal Euclidean distance between the points of the data set. Yes? So let's see this image here in order to better understand this. So these points, these blue points and orange points that we have here are the data set. And these stars that we have here are the centroids of the system. Yes? Then we can, calculate the shortest Euclidean distance to this centroid. It can be calculated with this equation here, yes? But, for instance, the shortest Euclidean distance from this point to this centroid is this one, yes? And the shortest Euclidean distance from this dataset point to this centroid is this one, yes? So this point is closer to this centroid than it is from this centroid. Yes? You see that? And this point, this orange point, is closer to this centroid than it is from this centroid. Yes? Then, since these dataset points are closer to this centroid, they are grouped here into a cluster. Yes? This is why they are marked with a blue color. Yes? Sorry, let me drink some. Then, on the other side, these two dataset points are closer to this centroid. So, they are placed here in a different cluster. This is why they have a different color. Yes? Then these centroids can move. Yes, will move in each iteration. We are going to see this in a moment, don't worry. So for instance, here we have the exact same dataset points in this image. Yes? These 2 points here, and this third point, which is here. The points in this image here and in this image here, the dataset points are the same, but the centroids have changed their position. Then, by changing their position, the clusters have also been modified, because now this point here, which here in the first image is closer to this centroid, in this second image, this point is closer to this centroid. So now this point has been assigned to a different cluster. So his color has changed from blue to orange. Yeah, makes sense? Sorry, let me drink some because I'm talking too much and my throat is getting very dry. Then, when we start to perform clustering, when we start the clustering process with the Cummins algorithm, the start position of these centroids is random. Yes, it's completely random. So we will have our dataset points, and then we will place the centroids in random positions. Yes, then while we start running the algorithm, the Cummins algorithm, for a specific number of iterations, the positions of these centroids are going to keep changing. Yes, they change and they will learn. Yes, so they are going to keep changing based on the experience from the previous iterations. Yes? Does this make sense? Then the number of iterations, basically it's the number of times that we are going to compute the whole dataset. Yes, so this would be an iteration. For instance, this image would be an iteration. Then this image would be the iteration n+1, would be the next iteration where the dataset we have is the same, but we have changed the positions of our centroids. Yes? Then the label, as we can see, the label would be in this case the color of the point, which is the cluster they are placed in. Yes, is given based on the shortest distance to the centroid, as we have seen in these images and we have shown here. So since this dataset point is closer to this centroid, then it is assigned to this cluster. Yes, to this label, let's say. Yes? Then in the next iteration, the centroid moves to a new position and we compute again all the clustering process in order to assign the dataset points to one cluster or another. Yes? Then this process finishes either when the number of iterations reaches the maximum. So if we define our process to have 100 iterations, then at the iteration number 100, the process will end. Or when the change in position of the centroid is almost negligible. Yes? So the positions at the beginning, the positions of the centroids will keep changing a lot because the algorithm it's learning. Yes? but then it can reach some point at which the position of the centroid is already optimal, so executing more iterations, it's not going to do almost any change in these centroid positions. Yes? So at this point also, the process, this whole process, will end. Yeah? Then, does it make sense, more or less? Yeah? Let me see here. This is my first class. Excited to get started, says Sagar. Okay, I'm excited that you are excited to start, Sagar. Welcome. Der Capute says, sorry guys and girls, I have to leave. See you next time. Well, I'm sorry, Der Capute. See you soon. Take care. Alright, then... Okay, so we have introduced more or less some basic principles of this Cummings algorithm and how all this clustering process with the different iterations works. So now let's do some practical examples. Yes, we are going to start here generating some plots here in the notebook itself. So first of all, here we have some Python code which is going to help us to execute the elbow method. Yes, remember the elbow method is a method which we can use in order to determine, to select an optimal number of centroids to use. Yes? Then, for instance, here we have a predefined dataset. Yes? Here we have pairs of numbers which represent in this case positions in the x-y coordinates. Yes? We have x coordinate, y coordinate. So here we have pairs of datasets which represent x-y coordinates. Then here we have here we define our dataset, and then here what we are going to do is to execute the k-means algorithm here in order to determine the recommended, the optimal, the ideal number of clusters to use. Yes? So let's run this example by selecting here the cell and clicking on the run button, which I have already done. Yes, then this might take some seconds because it has to compute everything. So let's wait here a few seconds until our plot is generated. You can see matplotlib is building here the plot. Here we have it. All right. So here I have the plot, which indicates the elbow method to estimate the ideal number of clusters. Yes. Then why this is called the elbow method? Well, super simple. Because the ideal number of clusters would be the elbow of this curve. Yes, here we can see that the curve has a lot of curvature here. Yes, but then it reaches a point which more or less would be here 4, 5. Yes, where it gets more linear. Yes, then in this case, the ideal number of clusters would be the elbow of this curvature, which would be more or less 4, 5 clusters. Yes. So in this case, the elbow method estimates that a good number of clusters to use for this given dataset would be 4 or 5. Yes. Then, however, now we are going to use only 2 clusters. Yes, for simplicity or for not charging too much these the processors. Yes, we are going to use for now only 2 clusters. Yes, and we are going to run our Cummings algorithm for 15 iterations. Yes, so here we are defining our Cummings class. We have it here. Yes, here we are defining the centroids. We initialize here in this function the centroids to random position, here using the rand in Python function. And then here we are defining the method to train the data set. Yes, the method in order to keep changing and updating, adjusting the centroid's position. Yes, depending on the Euclidean distance, the minimal Euclidean distance from the dataset points to the centroids, we are going to keep computing these distances and improving the centroid positions so that these distances are the shortest possible. Yes, this is the goal of this. Yes, so the goal is to have the centroid's position in a way in which the dataset points have the shortest distance to these centroids. Yes, so we would compute, let's say, the distance from the points to this centroid, the distance from the points to this centroid, and we will sum these distances. Yes, then our goal would be to have the minimum distance. Yes, this is basically what we are doing here. There we go. And finally here what we do is to so here what we are going to do is to plot the data set. Yes, so let me first of all come here. Okay, so we have computed here. Let's now run this cell, which is going to generate our Cummins class here with the functions. There we go, it has been executed, and now we are going to execute this other shell, which is going to basically plot the data set. Yes, so here we have all the points from our data set. Yes, so now once I start running the algorithm, which I'm going to do here, yes, so here is where basically I'm going to run the Cummins algorithm. Yes, I'm going to start running everything and all the iterations, and in this case I'm going to print, yes, the output so that we are going to be able to see it properly here. Yeah, so yeah, I have everything run, everything prepared. Then I'm going to run. So here I have my dataset points, and now my algorithm is going to start assigning centroids here. In this case, remember that we have defined two centroids. We are going to have two centroids and two clusters. Yes? Then for each centroid, let's say that first it's going to place one centroid here and another one here, let's say, yes, because this is random. And then it's going to calculate the distance from this centroid, the shortest distance from this centroid to all the closest points of the data sets. Yes? Right, let me just stop talking and execute it, because it's going to be easier to understand and to visualize. So let me come here to this cell and run it. There we go. So this is calculating, and here I have printed my results. Yes? So this would be the iteration number 1, iteration number 2, iteration number 3, etc. until iteration number 15, which is the last one. Oh no, here I have only 10 iterations. So instead of 15, I have defined here 10 iterations. Yes, so the iterations are 10 instead of 15. Alright, so I have 10 iterations. Then as you can see, here in iteration number 1, what the algorithm does is to place here two centroids. Yes, one here and another one here. This is random, yes? These positions have been assigned randomly. Then it calculates the distances to these centroid points, the shortest distances to these centroid points, and assigns the different points to each cluster. Yes? Then in iteration number 2, the position of these centroids is changed. So the clusters, the labels for the different dataset points also change. Yes? Here we can see the blue ones, here down the green ones. Yes? Now, here the centroid positions change again. Yes? So now we have here at the left side the greens, at the right side the blues. Here again the centroid positions change, etc., etc., etc. Yes? So this keeps changing, and it keeps improving, learning from each iteration and improving. Yes? So as you can see here at the beginning, especially, the positions change quite a lot, yes? But here at the last iterations, the position do not have a huge change, yes? So this one, for instance, is very similar to this one, yes? This one, the positions is very similar as well, but they only swap the centroids, yes? So here we have at the left side the blues, at the right side the greens. Here we have at the left side the greens and at the right side the blues, yes? But here we can see graphically with these matplotlib plots, we can see how these centroid positions keep changing, yes? On each iteration. Yeah, so far so good. So this is super interesting, yes? So without any external supervision, yes, the algorithm has discovered the location of the centroids which minimize the cost function, yes? Does it make sense, guys? Let me see here, I can see some comments. Access to the project is only available with subscription, right? No, it's free. It's free. So okay, I can see that Mikael has already answered you. Yeah, it's free. You just need, in order to be able to access this project, you just need to create an account in the ROS developers in the ROS developers studio, which is completely free. So you don't need any subscription. Well, yeah, it's a subscription, but it's free. I mean. Yes, it makes sense, says Lokesh. Okay, excellent. So now we have seen here some practical examples, and we have visualized some plots of how this Cummings algorithm work. But now let's try to do an example using ROS. Yes, because what we are basically is ROS developers, right? And this is called the ROS Development Studio. Yeah. So let's try to apply this Cummings algorithm to ROS and to robotics, and specifically to this robot we have here. So now we are going to do some practice, a very interesting practice where we are going to apply this Cummings algorithm and this process to our robot. Yes. Then for this, what we are going to do first of all is to insert some cylinders into the simulation. In this case, we're going to spawn 5 cylinders into the simulation, yes? And how can we do this? Super easy. We can come here to the Gazebo window, and here we have a tool. You can see here to insert box, insert a sphere, and insert cylinder. Then if I click here, I can insert a cylinder here in the simulation, wherever I want. So I'm going to insert, for instance, one here. I'm going to insert another one, let's say here. I'm going to insert another one here. I'm going to insert another one here. And finally, the 5th one, I'm going to insert here. Yes, so I have my Turtlebot robot completely surrounded by these cylinders. Yes? And now what I'm going to do is to run a script. Yes? Here with this command, I can run a script which is named run move laser. Yes, but let me have a look at this script. So what is going to do this script? So basically the goal or the purpose of this practice exercise is to discover the obstacles in the robot environment. In this case, the obstacles are the cylinders, and estimate using the Cummings algorithm the positions of these obstacles. Yes? So this is our goal, to discover these obstacles and estimate the position of these obstacles by using the Cummings algorithm. Yes? Then for this, we have first created and spawned our obstacles, and next we have this script. But let's have a quick look here. So I have opened here an ID window by coming here to the Tools menu and clicking on the ID button. So now here in the Catkin workspace, I have, inside the SOC folder, I have this package named live class, which has an SOC folder here, yes? Now, inside this SOC folder, I have a couple of scripts But basically, the one which I'm interested in is this one. Run move laser.py. It's the one that I'm going to execute. So let me open this script and have a quick look at it. So basically, as we can see here, I have a class which is called Robot Go, right? Here, previous to this class, I have a function which basically is a Python function to transform polar to Cartesian coordinates. Yes, from polar coordinates to Cartesian coordinates. Here we have it. Yeah. Then here in the class, I am doing two things. Here in the constructor of the class, sorry, I am subscribing to the odom topic, which provides the odometry of the robot, and I am subscribing to the Kabuki laser scan topic, which provides data from the laser of the robot. Yes. So here at the top of the Turtlebot 2 robot, I have mounted a laser, which obviously it's capturing data from the environment. Yes. So I am creating here two subscribers in order to get data from the odometry of the robot, from the coders, and from the laser of the robot. Yes. Then here I have the callback function for the laser, where I am capturing here the data. In this case, it's the beam, the laser beam 360, which corresponds to the data of the laser right in front of the robot. Yes. So in this case, I'm capturing the data of the laser right in front of the robot. Then I also have the callback for the odometry topic. Then here what I am doing is to capture, as we can see here, the orientation of the robot. Yes? And we are transforming this orientation from quaternions to Euler angles. Yes, so that we can process it easier. And finally then what I am doing is to give an angular z velocity to the robot, which is going to cause my robot to rotate on the z-axis. Yes, so my robot is going to keep rotating. Yes, it's going to keep rotating on its z-axis and capturing all this data from the odometry and from the laser. Yes, while it keeps rotating. And then at the end, when I stop this program, what I'm going to do is to write this data, as we can see here, into a file. Yes? So here I'm writing all this data into this variable. Yes? And here, this file1 variable, and here what I'm doing is to write all this data into a file. Yes? So I'm going to create here in my cacking workspace, I'm going to create from the program a new folder called results, and inside this results folder I'm going to generate a file called laserdatapoints.csv. Yes? So all this data that I'm going to be capturing with my robot, all this odometry and laser data that I'm going to be capturing while my robot is rotating, I'm going to save it and write it into this CSV file. Yes, which I'm going to write here in my cacking workspace. Right now I don't have it because I haven't run yet the program, but right now I'm going to run the program and generate this file. So yeah, let me come here, and well, first of all, I'm going to need, of course, to open a new shell in order to be able to execute the commands. Then I'm going to, first of all, source my workspace. Let me come here, copy the command and paste it here into my shell. And then I'm going to also copy and paste this second command, which is going to run this Python script that I have just reviewed right now. Yeah? There we go. So here I'm running my program, and now we can see here how my Turtlebot robot starts rotating. Yes, here it's doing the first rotation, and here it's printing some data as well. And here we can see that it has already created this results folder with this laser data points CSV file. Yes? So I'm going to leave it here do a couple more of turns. so that it has a bigger data set, yes? There we go. Let's allow it to do one last turn here, and then I'm going to stop the program. There we go. The last rotation, and I'm going to stop it. Alright, so I have stopped my program. The robot is going to keep moving here, as you can see. It doesn't matter, you can leave it turning. It doesn't affect nothing that the robot keeps moving, because what we wanted to do is to just capture the dataset. Yes? So we have already captured the dataset while it was rotating, and we have saved here this dataset into this laser data point CSV file. Yes? So I can open here this file, and I will see that I have all the data here into this file. Yes? So all I wanted to do is to generate this file. Yes, so this is what so now I don't care if the robot keeps moving. In any case, I'm going just to stop it here by publishing into the command belt topics directly here, 0 velocity, so that it stops. There we go. Alright, so now we have our CSV file with the data that we have captured while the robot was rotating, yes? Then, what are we going to do now? Well, what we are going to do now is to, of course, use this data in order to apply for our K-means algorithm. Yeah? Does it make sense? So, first thing that we are going here is to read this file. Yes? This laser data point CSV file that we have just created here, we are going to load it. Yes? In this case, I'm going to load it into the system, and we are going to plot it. Yes? So let me come here to this cell and press on the run button. There we go. And here, I have loaded from my file all this data, and I have printed it here into a plot. Yes? So here I have the data that I have captured from the file, which, as you can see, it's a representation of my obstacles, right? So here I have all the points that the laser basically has detected these obstacles while I was rotating the robot. Yeah? Then, what else? Next thing I am going to do is to run the elbow method in order to get the ideal number of clusters that I should use. Yes? So let me come here and run as well this cell, which is going to generate. Here I have it. And here I have generated the elbow method. So as you can see, in this case, it's super clear that the recommended number of clusters is 5, which in fact makes sense. Yes? Because we have 5 very defined dataset points. Yes? My dataset points are very defined into 5 different areas. So it makes completely sense that my elbow method tells me that the ideal number of clusters is 5. Yes? So for a higher number of clusters, in this case 6, 7, 8, you can see that the difference from all these clusters to 5 is minimal. So it makes no sense to use more than 5 clusters. Yeah? Then, what else? Here, what I'm going to do is to run my K-means algorithm. Yes? So here I defined the number of clusters, which is 5. The initialization is random of the centroids. I have here the number of iterations, etc. Max iterations, in this case 300. Yes, but I'm going to run at the end. I'm going to run. I think it's going to be 10 iterations. I think. Well, I'm going to see now. All right, then here in the final, okay, yeah, so here basically I'm going to run the K-means algorithm, so let me do it super quick. Yep, here I have run my K-means algorithm, And now here what I'm going to do is to print the result. In this final cell, I'm going to print the result. So let me click here on the run button, and there we go. Here I have printed the results, yes? So here I have all my datasets with the final ideal position of the centroids, which, as I can see, it has predicted super well the positions of these obstacles, yes? So my centroids are placed exactly at the center, yes? Here, at the closest point to from the obstacles to the robot, yes? So it's amazing, this, yes? So we have captured our data from the simulated environment. In this case, it's simulated, but this could be also a real environment, of course, because we are capturing this data from ROS topics, yes? So it doesn't matter if it's a simulated robot, a real robot, yes? Then, with this data, we have calculated first the ideal number of clusters using the elbow method, and then we have run the K-means algorithm here using the K-means model for a certain number of clusters and for a certain number of iterations, and then the K-means algorithm has approximated, here we have, has placed the centroids in each respective obstacle, yes? Then now we could use this information. For instance, we could use the centroid's position information in order to feed it to a motion planning algorithm, in order to create a obstacle avoidance algorithm, or something like this, yes? Alright, excellent, so that's it. So I encourage you guys, if you want to play with this, so you can add more obstacles, you can add, for instance, I don't know, boxes, spheres, you can add more obstacles, place them, move them from one position to another, and play with all these, yes? Like this, you can move them from one position to another, whatever you want, you can do, but I encourage you to play with these and experiment and see how the results vary, yes? But yeah, basically that's it. We have finished this live class, so mission completed, yeah? Then thank you very much. Let me have a quick look here at the chat. Is it possible to simulate a cracked wall in Gazebo? Yeah, of course. It's possible. If you generate the, if you have or generate the models, you can simulate it. You can simulate a cracked wall in Gazebo. Shayak, yes, it's completely possible. How does one determine the optimal number of clusters when looking at the graph produced by the elbow method? Okay, very good question, Ben. So, as you can see here, this is the elbow method, the graph that we have from the elbow method, yes? Then here we can see that there are big changes in the curvature, yes? But this curve reaches a point, which is, in this case, it's the number 5, yes? Here, these points are the number of clusters, yes? Here it's 0, 1, 2, 3, 4, this is 5, 6, 7, 8, 9, 10, yes? You have here the index. So, and here we have the distortion in this case. So as you can see, the change in the distortion from having one cluster to having two is very big. Also from having two to having three is big as well. Also from having three to having four, there is a big change. And from having four to having five, there is also a quite significant change. But from 5, as you can see, the change is minimal. So in this case, the elbow of this curvature would be the number 5, because from the number 5 on a higher number of clusters, there is no significant change here in the curvature. Yes? So this is how we would determine the number of clusters. In this case, ideally it's 5. Yes? And we are then setting here the number of clusters parameter to 5 in the K-means definition. Yeah? Thank you, says Michael. Thank you, Engineering Nation. Okay, so thank you guys. Thank you very much for assisting to this live class. I hope you have liked everything that we have done here. I think it's super interesting, honestly, from my point of view. I think it's super interesting to be able to analyze these machine learning's concepts, in this case the Cummings algorithms, and being able to apply them here to a robotics, real life robotics example. In my opinion, this is super interesting and super amazing. So I hope you think the same way as I do. And if you would like to learn more about this, as I have already said before, I really encourage you guys to have a look at the machine learning course. Yes, so I have already mentioned this before. But if you liked this live class and you are interested in learning more, not only about this algorithm but many others, also neural networks, etc., have a look at this machine learning for robotics course. Yeah. Also, if you would like to support us, you can do it by subscribing to our ROS Online Academy, as you already know, here where we have all the courses, as I already have explained it. You can also, here I have a link in case you want to go directly. Here I have placed a link to the machine learning course. And also you can buy one of our ROS developers MOOCs, yes, like the one I have, or a ROS developer shirts. And finally, please, you can also give us a like on YouTube and subscribe to our channel if you aren't subscribed yet, which also helps us, and it's completely free. So yeah, guys, this is going to be all for today. Thank you very much. I hope you enjoyed the live class. I hope you have learned at least something new. And I will see you next Tuesday with live class number 98. Yes, then until next Tuesday, take care and keep pushing your ROS learning. So bye bye.